make a simple raycast application from scratch. The idea is that we have this tiny little drawing application where we can draw, and basically what we don't see is that we're actually drawing on these walls, so that basically our thing gets raycast and gets cast into these weird little angles. So whenever we draw, it looks like we're drawing straight on, but then if we move back, it seems that we're actually drawing on these walls. It's actually simpler than it looks, and the main trick is that we can do raycasting, and that's what we'll explain in this video. So I built this from scratch before, but I'm going to build it once again. So I'll call this let's call this invisible walls, and I'm just making a new folder that's completely empty, as you can see. And then in that folder we're going to add some dependencies. We're not going to use npm or anything like that. We're just going to fill our folder with dependencies. So what I like to do is, because we're using THREE.js, is I'm just going to go to unpackage.com and type /tree. So that's the THREE.js package, but I want a minified one, so I'm going to type min.js, and that's a file that I want. Now Safari actually doesn't really allow me to download that, so I need another browser, for example Chrome or Brave or Firefox. That all works. So I'll go put that here, and now while we're at it, we're also going to get rid of that part of the URL, and then I'm also going to copy a couple of other files from the examples folder. One is the orbit controls, which we need to rotate our view. So they're in examples, JS and controls, I think. You see this takes a while. Orbit controls, this one. And then once we have that file, we choose view raw, and then we save that. And I think for our purposes, this is all we need. So we don't need any other files except for those two. So we'll double check that these are here, right? We'll also make a JS folder while we're at it, and maybe a CSS folder as well. Right, so now everything's set up to open that up in Visual Studio Code. So in Visual Studio Code, what I'm going to do is open that folder, choose a desktop, invisible walls, and this is my completely blank canvas. So I'm going to start by creating a new file here, index.html, and I'm going to let Emmett do most of the work for me. So type exclamation mark, and that gives me the basic structure of my document, as you can see here. The idea is that we don't really need much inside of that document. We just need the name, like invisible walls, like this. We probably need a link to our style sheet, which we haven't created yet. And then in our body, we don't actually need anything except for some script tags. So I'm going to flesh this out. I'm going to make a file main.js in JavaScript, and then maybe also make a main.css here. The CSS is basically empty, so all it needs is a body tag where we say the margin is 0, and because we want to use the whole canvas, the overflow is hidden, so we don't want any scroll bars here. That's it. And then for our JavaScript, we'll do that later, and then here we just link to all these files. So I'm going to type script:/source. That's going to link to our third-party script, first stream.min, and then also going to link to third-party orbit controls. Make sure that the order here is important, because orbit controls depends on tree being there, otherwise it doesn't work. And then finally we're going to also link JS main.js, so that's our last file. That's our renderer, and that's the thing that we're going to stub out with our main rendering loop. If you're completely new to THREE.js, this might go a bit over your head, but in the THREE.js getting started guide, there's actually a really good introduction into how you make this main file. So this is creating a scene, this basic thing, and I like to start with something that looks very much like this, so we get the basic setup, and the moment I have a cube running, then I'm sort of confident that I can do the rest. So we'll get the cube there first, and then we'll do the rest. Now this will need a couple of functions, so we'll type a function in main.js. We have a setup function that's basically going to render out all our JavaScript, set up our scene, our camera, add some walls to that, add some lights, things like that, set up the renderer. and the raycaster, and then we have a render function that actually just renders. It's super simple. We have an animate function that animates our scene if we want that, and then we have some mouse functions that basically react to the mouse so that we can draw. We'll do all of these step by step. So for our setup, what we need is we need a camera, and I'm going to specify a number of variables at the top here, and those are the ones that I want to be able to access globally, and that's why I add the G here in the front. So I know that the camera is going to be a global. It's going to be a new tree, and that's going to happen a couple of times because he doesn't know what THREE.js is camera. We give it a field of view, so 60, the aspect ratio, which is the inner width divided by the inner height, and then we give it a near and far plane, so how far it can render. This is not super important that these are exactly these values. You can play around with those, especially the field of view is interesting to see what that gives if you change that. What is important is that we set a camera distance. So we're going to say the camera has a certain distance from those walls, so like 5, and then we can say the position of our camera is going to be set to that camera distance in 3 directions. And then we're going to make that camera look at the center of our world, so look at 0, 0, 0. So it's basically far off and or 5 units off, and then it's looking right at the center. So that's our camera. Now let's set up our scene. So again, we make a global here, gScene, and here we're going to initialize that. So gScene equals new tree dot scene, and let's add some things to that scene immediately. Let's add some lights to that. So those lights don't need to be global because we are adding them here, but we're never changing them. This is from an example that I saw with raycasting hemisphere light. It basically gives this nice overall glow. You can use these values. We can just also type white if you want. And this is the I don't know, the second color or something, secondary color, and this is the intensity. We're going to set the position of that light. Again, feel free to play around with those, and then also add that to the scene. So that's light 1, and we do that again another time for a secondary light. So this is all light 2, and then here we're going to leave those as is, but we're going to have to put a little bit less brightness, and then that's it, I think. It's kind of weird that they're in the same position. Maybe we can just do this and put it somewhere else. Okay. As I said before, I just want to see some kind of cube or box or something in the middle. So what I'm going to do is just do the basics, and the basics is just have like a box geometry, which is just a new tree.box geometry. No, like this. We also want a box material, which is in tree is a tree mesh Fung material. We're using Fung shading here because it's super simple, but also note that Fung shading actually is influenced by lightning. So if we don't have any lights in the scene, all these objects will appear dark or not at all, because there will be black against black. So we really need that. And then we're going to add a mesh. So box mesh equals new tree.mesh, which is a combination of geometry and the material, and then add that mesh to the scene. Right, so we have a scene that has a 2 lights in them and a box. That's kind of okay for now. We also want a renderer so that we can actually see the scene. Again, we want to initialize this at the top because we want to be able to access it from everywhere. That's a new tree.webgl renderer. We probably want anti-aliasing so it looks a bit nicer. And then we want that renderer to set the pixel ratio. That allows us, if we have a high density screen, to actually see that, and that's especially important on phones, for example, which all have high density screens. And then set the inner width and the inner height to the size of the renderer. And then we basically want to append our canvas here. So that's going to put that canvas on inside of the screen. Now we still have to call setup. So if we call setup here and we use go live to actually start, I think Safari in this case, we see that our entire screen is black. So it's filled up with this canvas here, which is good. I do see that we have an error here. It's missing an icon. We don't really care about that icon. And then also there's a animate function. So we're going to animate our thing continuously. So we have to write that animate function. And that animate function is very simple. It's something that you see in all the tutorials for Three.js. Basically what it's doing is immediately asking for another animation frame like this, and then it's going to render like this. And for the render function, that's also super simple. All it does is just call the renderer and say render the current scene with the current camera. Right, so that's our basics out of the way, and if everything goes right, we should see this little box here. So that's actually showing up. If we don't see anything, go check the console to see what's wrong. One thing that you see immediately is once you resize the window, nothing happens. And that's because we are not updating our viewer. So we also have to add a listener here, an event listener for the resize event, and then call like on resize. And that's another function that we have to create on resize. And what that's going to do is change the camera aspect ratio. So because the width and height are no longer the same dimensions, we have to make sure that we change our aspect ratio so not everything gets stretched. And then call update projection matrix, and that's going to make sure that the camera is up to date. And also for the renderer, set the size to the new window size, so window inner width, window inner height, like that. So now we should be able to resize our window and everything should follow nicely. Cool. Right, it would be cool already if we can drag this around and actually see our box, and for that we're going to use our orbit controls. So we're going to make another one at the top here, controls. And then also here, right before the renderer, we're going to say, let's initialize our controls here. We can actually do it after the renderer here. G controls equals new tree.orbit controls. And the orbit controls require the camera and they require the renderer.dom element. I'm not sure in this specific case if we do need them in animate node. I think this just works. Super cool. So now we can drag this around with left mouse button and do all kinds of things. We will get into trouble later because the mouse and the left mouse we actually want to use to draw. So we have to remap these controls, and to do that we're going to say the controls have the mouse buttons here. And here we're going to say the left mouse button is actually set to null, so nothing happens on the left mouse button. The middle mouse button we're going to use to pan, like this, and then the right mouse button we're going to use to rotate. If we don't set that, then two things will happen. So as we drag on our canvas, it's going to influence both the controls and the drawing, which is super annoying. So now if we press the left button, nothing happens. We can drag with this button, the middle button, and then we can pan around with right. So that seems to work. Another thing, this is the basic setup, so we're sort of done right now, I think, with the basic setup. What we need right now is the actual wall, so the things that we can draw on. And the way that I'm going to set that up is I'm going to make a little group called G walls. And that group is going to contain all my walls. And basically I want to raycast against all those walls. And while we're at it, we'll also make the raycaster here. So I know this is a new, a lot of these things are new, but let's talk a little bit about those walls that at least should not be new. The idea for the walls is that we make one material for the wall and one geometry, and then we're going to just make meshes that you all use that same wall geometry. Now, first off, I'm going to make a Fong material just because it's sort of clear with the reflections, but I want to change this to a basic material so that we actually don't see any light bouncing off, so it's harder to tell where the walls actually are, which is kind of the point of this this little project. And then the walls are just a box that we stretch. And then the G walls is actually a group of walls. So this is all of the walls go inside of that group. So we're going to make a loop. So we're going to say while I is smaller than 3, let's say, let's add 1 to I, and then for all of them we're going to make a tree.mesh with the wall geometry and the wall material, like that. And then we're going to scale that wall because the wall is now 1 by 1. So we're going to set the X position to 1000. So that's the main edge of our wall. The Y position, the height of that wall, is going to be 10, and then the thickness of that wall is going to be set to 1. Every wall needs to be rotated and positioned in a different position. And to do that, we're going to make a small random function that I'll add here at the top. And we can use mod random. This does in fact use mod random, but it just makes it so that we can provide a minimum and maximum immediately. And all it does is says, well, mod random gives you a value between 0 and 1. Let's multiply that by the amount of numbers that we need. And so how much do we need? Well, we need max minus min. That's the delta. And then we get a number between 0 and the size of the number that we need. We need to add min to that. And now we have a random number generator between min and max. Super easy. Let's set the rotation here. And we want to rotate in Y, so that Y is going to rotate our wall. So we want to rotate a random value between 0 and mod pi multiplied by 2. So this is basically a full circle, so it can rotate in any direction. And then X is not rotated and Z is also not rotated. And then we do the same for the position. So we don't want them all in the same position. Instead, we want to basically give them here some random positions so that the walls are all sort of positioned a bit randomly. And then we don't actually add them to the scene, but we add them to the walls group, like this. And then finally, we're going to add that walls group to the scene, like this. And if all goes well, and it does, then we see that we get all of these walls here. And so every time we refresh, we see that we get a different configuration of walls. Cool. So with that working, we don't actually need this box, so I'm going to comment that out. And now it's time to do the actual raycasting, I think. So the raycaster we're going to initialize here, and we're going to look at that while we can actually see what the code is doing. It's much more useful than trying to explain what it's trying to do. The idea is that we're going to do those things the moment that we use or move our mouse so that we can actually drag. So to do that, we need to capture mouse events. And the way that that works is we're going to listen for mouse down, mouse move, and mouse up events. And mouse down is the first one. And here we're going to make a function called onMouseDown. We're going to add that here. So an onMouseDown does is it's going to check if we press the left mouse button. And then we do that by if e.button is not the left mouse button, then we immediately return. We jump out of this function. We only want to capture left mouse buttons. And then all we do here is we add an event listener for mouse move. That's going to be called onMouseMove. And we do the same thing for mouse up. So mouse up, we're going to call onMouseUp. So onMouseMove, that's the most complex one. We'll leave that here for now. And then onMouseUp, all that does is basically remove those listeners. So onMouseUp is going to remove those listeners. And the reason why is because we basically want to capture drag events, but we don't have access to drag events immediately. So instead we have to click when the mouse is down, we add listeners, and we know that as long as we get these mouse moves, we're actually dragging. And the moment we release our mouse, we get an onMouseUp event, and then we remove those listeners. So we no longer receive onMouseMove events. That's the basic idea. So each move event gets this event object, and that event object is going to capture the mouse position within window coordinates. So we can actually log that out so you can see what happens. So e.client x and e.client y is going to map the position of the mouse. So if I drag here, you can see that these values change. So they're really high here in the end and really small here in the beginning. Cool. Now, if we do raycasting, the positions that we need are not actually from the coordinates of the window, because those can change, but they're in coordinates that are in normalized device coordinates. Basically, they're numbers that need to go from -1 on this end to +1 on this end, and -1 here at the bottom to +1 here at the top. So we need to convert those, and it's kind of tricky to do that with these values, and the best way that I found is to write a simple map function that's basically going to convert values from a certain range to a certain range. So we're going to say, well, here's our value, and this is where the minimum and maximum are of these input values. So if you think about this, our minimum and maximum input values are between 0 on this side, and the maximum is the width of the window, so on this side. In this case, 1238 pixels. So that's our input range. And then our output range, in this case, needs to be from -1 to 1. So if we can write a function where you can just say, okay, here's our value, this is the range where it's in, and this is the range that needs to go out, then we can use that function for everything. So it's super useful. And it looks like this. So it first converts a value between 0 and 1.0. So it's basically going to take that value and then find out where is it on that in minimum and maximum bounds. So it's just changing the value here. So it's saying value minus in min divided by in max minus in min. So again, just like we did here with the max and min, we're looking at the delta of that value, and then we're going to find out where that value is on that on that delta on the rest that we have. And once we have that, we're going to convert to output range. So our value here is between 0 and 1, and then now we're going to say, well, here's the same. So this is basically the same as we did with our random, but here we're going to plug in our value. So we're going to say value is out min plus the value multiplied by out max minus out min. And as you can see, it's kind of similar to what we have here, right? Min is this min plus here's a random value between 0 and 1. Here's a value between 0 and 1 multiplied by max minus min. So that's our value, and then we return that value. Cool. So this is a very useful function to have, and I use it all the time. So where do we plug that in? What were we doing here on mouse move? We're going to say, well, the mouse x position equals the map of e.clientx, so that's the position of the mouse, and that value goes between, so the input here is between 0 and window.innerWidth. The output is between -1 and 1. So now we have a mouse x position that's between -1 and 1 at the end of this function. And we do the same for y. We can copy, but be very careful to make sure that you have everything set up correctly, because it's very easy to make mistakes here. So this needs to be client y, that's what we're listening for. This needs to be the height. And then here, the coordinates actually are flipped. So the -1 coordinate, the lowest coordinate, is actually at the bottom of the screen. So here we need to flip those. The 1 goes here and the -1 goes here. And that's our mouse x and y position. Now, if we do raycasting, we need a vector. We need a THREE.js vector. So we're going to make a THREE.js vector out of those by saying tree.vector3, mouse x, mouse y. And what's the z? What's the depth of our mouse position? Well, we don't really know. So we can basically put anything we like here. I'm just going to put 0.5 here, but you can try changing that value, see what happens if you make this larger or smaller. Right, and now comes the, let's say, the magic part. So now we are going to ask our raycaster to do its magic. So we're going to say raycaster.set from camera. So take this mouse vector, take the camera, and then basically project that ray. So find out where it has to rotate, so coordinate that that angle here, right? And with that, we are projecting that ray, and now we can intersect. So the idea of the raycaster is that it's going to find a position in 2D space, going to project that out into infinity, and basically going to tell us where it's going to hit. So if our ray comes this way, it's going to hit this wall, and then it's going to hit this wall. Not only is it going to tell which walls that we're hitting, but it's also going to tell us the exact position where these rays are hitting. And this is super useful because we want to add a little box exactly on that position. So that's the main idea here. So we're going to ask our intersect. So we're going to ask our raycaster to intersect objects. And note the plural here, the S at the end, because we want to intersect with all our wall objects. So it's G wall, so that's our group here, and then we can ask the children, and that's an array of walls basically, and we can ask it to intersect. Cool. So we hope that we find something, and we can log that out to see if we actually have some intersects. So if we click here, we see that we get some objects here. I'm going to turn off this one. If we click here, we don't get anything. If we click here, we see that we have multiple objects that we're clicking. So up to 3 walls that we can hit at the same time if we're aiming for the right point. So that's really cool. What's also interesting is that they're sorted. So they're sorted by distance. So this is the first wall that we hit, then this is the second one, and this is the third one. So it's giving us the distance, and then it's also giving us the exact point in 3D space where we actually hit that object here. So we get the object itself, so which object did you hit. So for example, we could select it that way, and then also it gives us a point where that actually hit. So super useful. So we're going to ask if intersects.length is bigger than 0. So if we actually intersect with an object, let's take the first object that we hit. Let's call it first intersection equals intersects 0. And then we want to place a object at that position. And to do that, what we're going to do is, because we don't want to make a box geometry every time, just like with the walls, we only want one box. So what we're going to do is we're going to do a bit of preparation here. We actually had a box geometry here, and we had a box material here. What we're going to do is make those global. So we're going to say G box material, and also G box geometry. And then we're going to take these out, and we're going to call this G box geometry and G box material. So these are needed to make a mesh. So the mesh here is going to take in geometry and material, but we don't want the mesh to be created here, but we want it to be created for every time we actually have a mouse event here. So these objects can be reused, and that makes it much faster to actually render all of these objects. So whenever we hit an object, what we're going to do is make a new mesh called tree.mesh with that G-box geometry and G-box material. And we're going to take the position of that intersection point. So first intersection dot point, remember that's this point in 3D space that we have, and we can copy that. And the way that we can do that in THREE.js is we can say, okay, we have a position vector here. Let's copy the information from our first intersection point into our own position. So it's basically saying the position of the mesh is now the position of that point. And then let's add that to the mesh. Let's add the mesh to the scene, and let's see what that does. So now we can draw. Cool. And then we can zoom out, and it's actually already working. That's really cool. One thing that you notice is that in the original thing that I showed you is that the size of these objects are actually different. So here you can see that they're going smaller and then bigger. So there's a last trick that I did here, and that trick is to actually use that intersection distance as well. So the distance actually tells us how far away we are from the camera. That means if this distance is really large, then the object should actually be quite large, because it has to appear the same size than if the object is really near to us. So really near objects should be smaller in reference to far away objects. And that's really easy to do. What we do is we scale our mesh using a number, and we can do that using multiply scalar. So that's going to multiply the x, y, and z scale with that with a certain point, and that point is going to be the distance. So first intersection dot distance. Now, not exactly immediately the distance, because now if we draw, they're way too big. So we have to multiply that by a certain value. Let's try 0.1, for example. That's maybe a bit too big. 0.05. Let's try again. And now you see that the size always remains the same, even though if we zoom out, we see that these boxes at the very end are actually much bigger than these boxes in the beginning, which is cool and exactly the point. What I also really like about this is that you can actually use the height as well, so you can draw over the sizes of these boxes, and it just continues working. That's super cool. So now if we draw, it's sort of really stretching out here. Finally, what I said is that the material here sort of gives it away, right? The lighting of these walls actually gives the trick away. And the trick here is for the wall not to use the Fung material, but to use a basic material. And in the basic material, we can actually specify a color, like white, for example. And basic material doesn't have any effect for the lighting. It's just white, 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 white. So now we can draw, and then once we start dragging, we see that actually has an effect. But the walls are just plain, and you only can tell by these side views, which you can solve by making much larger walls, for example. So I think that's it, actually. I think we made the whole wall intersection thing work. As you can see, the whole raycasting thing is not actually that complicated as the name sounds. We can just basically draw wherever we think these things need to go. That's pretty straightforward. Setting up the scene is also, there's not much new going on if you're used to putting things into THREE.js. So that's it. I hope this was useful.